Hello students, in this video we'll discuss properties of the reciprocal set of vectors for a given set of vectors. So recall that if we're given a set of vectors, given a set E1, E2, and E3 and R3, a collection of vectors, that is a basis of R3. We define its reciprocal set of vectors by the upper notation, by E1 upper is E2 cross E3 over the determinant of E1, E2, E3. We define E2 upper symmetrically by E3 lower, right? Lower. E3 lower cross E1 lower over all the lowers. E1 lower, E2 lower, E3 lower. And then finally E3 upper as E1 lower cross E2 lower over the determinant of E1 lower, E2 lower, E3 lower. Where of course that notation, the denominators of all these things are just the determinant of E1, E2, and E3, which is non-zero because it's a basis, right? Okay, excellent. And so now let's prove some propositions that are related to this, this reciprocal collection of vectors. Here's the first proposition, prop. I know that E1 lower cross E1 upper plus E2 lower cross E3 upper. E2, of course, that's a 2, not a 2, plus E3 lower cross E3 upper is the zero vector. Okay, so let's prove something like this. So let's look at these things in sequence. Notice that each of these things has a determinant in the denominator, so I'm going to pull that out. So in other words, this left-hand side over here is going to be this determinant, E1, E2, E3 to the negative 1. They each have 1 in the denominator. Then we're going to have a what? Then we're going to have an E1 lower cross E2 cross E3, like that. And then plus what? And then the plus, the next thing is going to be a E2 lower, and then cross E3 cross E1. And then finally a plus E what? E3 lower cross E1 cross E2 like that, okay? Now I'm going to use the back-cab identity. Let's call it the back-cab identity is. Back-cab says that if I do A cross B cross C, this is back. And then cab. We proved that in a previous video, the back-cab identity. And so I'm going to use that 3 times, right? And so I have this determinant on the outside, so I have E1, E2, E3 to the negative 1. Then I'm going to do back cab over here. So back cab is going to be what? What's my B? My B is E2, so it's going to be E2, and then dot what? And then E2 in the direction of what? E1 dot E3, E1 dot E3, whatever that happens to be. And then minus cab, so that's minus E3, then an E1 dot E2. This next term over here is exactly what? It's going to be back, so the B over here is E3, so I have an E3, and then E1, E2. And then cab, so cab is going to be an E1, so minus E1, and then E2 dot E3. And then finally I have back cab, so that's going to be an E1 positive, E2, E3, minus cab, that's going to be an E2, E1, E3. That's a lot of writing, but let's see what happens over here. Let's look at this E3, look at this E3 over here, and this E3 term over here. Those are equal and opposite, so those cancel out. E2 over here, and then E2 over here, those are equal and opposite, so those cancel out. And this over here are equal and opposites, so they cancel out. And lo and behold, this is a non-negative quantity over here, so this whole thing is equal to 0. So in other words, we've proven our result that this, in fact, symmetrizes to 0. Okay, so in other words, when I cross the covariant component with the contravariant component and sum them up, so in other words, concisely we can say that EI cross EI upper by Einstein is equal to the 0 vector over here, right? Excellent. All right, excellent. Now what's the next result? It gives sort of credence to this idea of reciprocal collection of vectors, right? Namely that the determinants of these things multiply to 0, right? And so here's the next proposition, prop. E1, E2, E3 times the determinant of E1 with an upper, of course. So force of habit, right? Takes a little bit used to getting all these uppers and lowers, right? And just muscle memory. E2, E3 is equal to 1. Okay? And so I need the following result from this. I need the following lemma. So the lemma, which we've proven previously, just using backcab basically, is if I do A cross B cross C cross D, that's A, B, D, C minus A, B, C, D. Okay, that's one of our vector identities. Okay, it's easy to prove, of course, right? You just use backcab with A cross B, and of course you can symmetrize this both ways too and get a symmetric form of this as well, right? That's an easy exercise. And so now what we're going to do is how we're going to prove this. So I need a formula basically for this guy over here, right? And so if I look at E1 upper, E2 upper, E3 upper, well, each of these things has what? Has a determinant in the denominator. So I have to pull out 3 copies of that determinant, right? So this is going to be 3 copies of E1, E2 lower, E3 lower to the negative 3 power, right? Because I have 3 in the denominator. And then what are we going to have? We're going to have this expression. We're going to have E2 cross E3. It's the determinant, right? The determinant is the triple scalar product, right? So it's going to be the first vector over here, dot the cross product of those 2 vectors, right? So the cross product of E3 cross E1 cross E1 cross E2, like that. Okay? Excellent. That looks like a nightmare, but it's actually quite simple. Okay? Let's figure it out. So what we're going to have over here is this is going to be E1, E2, E3 to the negative 3 power. Let's leave this E2 cross E3 out here. Okay? And let's use our identity, right? So our identity says this is going to be what? This is dot product with what? So it's going to be A, B, and then D. So this is going to be an E1, determinant of E3. So that's my A, E3, E1, and then an E2, that's my D, right? E2. In what direction? In the direction of C, which is E1. Okay? Minus something that's going to be irrelevant, and you can sort of think about why it's irrelevant in a second, A, E3, determinant of A3, and then B, which is going to be an E1. And then what's the next thing that happens? And I put a C over there, but C is equal to 1. In the direction of what? In the direction of D, which is E2, right? But there's a determinant whose 2 columns are the same, right? And so that determinant is just going to be 0. Okay? Good? And so now let's think about what this thing is over here. So I have how many copies over here? This is going to be E1, E2, E3, lower, 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 to the negative 3. And then what? And then I'm going to have this E3, E1, E2 coefficient, and then times what? And then the dot product of that is going to be it's really E1, E2, E3, right? By commuting the dot product, E1, E2, E3, so that's 1 extra copy of that, which is good. And now the only question becomes is, what is this determinant over here? Well, if I flip the 3 and the 1, that's 1 cycle, so it gives me 1 negative 1. And then if I flip the 3 and the 2, that's 2 cycles. So if I do 2 column interchanges, I can change this into E1, E2, and E3. So what this is over here is this is just E1, E2, E3 to the negative 3 times E1, E2, E3 to the negative 2, which is just E1, E2, E3 to the negative 1. And lo and behold, if I look at the determinants of these contravariant or reciprocal set of bases, it's exactly just the reciprocal of the covariant basis. So in other words, when you multiply those 2 things, you have to achieve 1, which gives sort of a good intuition for why we call this the reciprocal set of vectors for a given covariant basis of vectors of R3. Now, in further videos, we're going to see how this idea of covariant and contravariant extends not just from 3-dimensional space, but to higher dimensional, n-dimensional Euclidean space. And we'll also encounter these ideas of contractions in more general tensor settings and more general settings when you have a tensor of higher order and contracting on 2 of the indices as long as one is covariant and one is contravariant. And so the labeling of covariant and contravariant will become very important in the further discussion of these tensor relationships. Thank you very much.